Hey guys, this video is an introduction video on psychrometrics. We're not going to get into any of the processes for psychrometrics here, but what I'm hoping to do is introduce you guys to a bunch of the different terminology and give you a base impression of what it's going to look like. This is the video that I'm making for the lab, so we'll probably be a little bit faster than we are when we go through class, but it's a good refresher nonetheless. Towards the end of this video, we will get into the psychrometric charts in particular and how to use them and where things are, and do a little bit of comparison between the by hand version and the chart version for our psychrometric calculations. With this, what are psychrometrics? Psychrometrics are problems with a combination of air and water for our system. So in thermodynamics so far, you guys have done a lot of different pieces where we're looking at just water and we're looking at systems that have water in them. We've looked at systems with just air in them or different systems with nitrogen or anything. But this is a system with some combination of air and water, which is real air. So there is all kinds of different combinations of these airs and waters, and we need some way to keep track of them, and we can do it by hand, and we'll talk about what doing it by hand looks like and kind of get a little bit of a view of what it's going to look like if we were to do some other combination of chemicals. But there are a lot of shortcuts that are made for psychrometrics because it's just so common to have air with different levels of humidity involved in it. So with that, before I get too far, I'm going to quickly show that we have a handful of subscripts that we're going to be seeing. So with this, we will be using these values, these subscripts, to mean the same thing throughout this video and the following videos on psychrometrics. So we are going to be talking about air. So if we have a subscript A, that is going to talk about air or dry air, meaning that there is no water moisture in said air, is only the air that is just air. We're going to talk about water. This subscript I don't think is going to show up in this video, but this is what we will use when we're talking about water. And then we have a subscript for vapor or water vapor, which we will also use. So these combination of three subscripts are going to be pretty consistent throughout here, and I will often shorthand using one of these three things, so it's important you know what those are. So with this, when we talk about our different systems, we are going to talk about several different terms here. The most common thing is our dry bulb temperature, or TDB. Our dry bulb temperature is simply our temperature. Sorry, catching up there. This is the temperature of our overall mixture. This is what you would get from a thermometer. If it says our temperature is 30 degrees, then our dry bulb temperature is 30 degrees. And for this, I know I've got this TDB. Oftentimes, we're just going to write our temperature, because when we're talking about temperature, we are talking about the dry bulb temperature. Now, the reason we have to designate it the dry bulb temperature is because we also have a TWB, and this is the wet bulb temperature. So this is the temperature if it's raining. So this is the temperature when we are talking about saturated air, meaning the air can hold no more water and it is going to have to let water go at that point. So this temperature is going to be exactly the same. We'll put temperature dry bulb is going to be equal to the temperature wet bulb when raining or precipitating. Let's see if I can actually spell that right. So after a certain point in temperature, the air is no longer going to be able to hold any more water, meaning that at that point it's going to start raining, or it's going to start condensing on the edge of glasses or on our windshields of our cars or on the grass with morning dew. So we have these two values that are equal when we have the maximum amount of water in the air, but are not equal. So any other time our temperature dry bulb is going to be greater than our temperature wet bulb. So just to kind of describe these, what this is describing is if you're standing and you are just chilling out on a 40-degree day, quite hot, hanging out next to the swimming pool, it is going to feel like it's 40 degrees. Now, if you go in and you jump into the swimming pool and then get out of the swimming pool, so you're sitting there and there's water dripping off of you, it is not going to feel like it is 40 degrees. It is going to feel like it is colder because you are wet. You have water that is evaporating off of your skin. That is going to require some energy release, and it is going to pull some of that energy from you, which is effectively going to be cooling you off. It's the same reason when it's super hot, we're going to sweat. We're going to release water, which is going to evaporate off of our skin, and that is going to make us feel cooler than the temperature actually is. With this, we have this extra piece that we're talking about. This is the wet bulb temperature. And we can actually physically measure this. What we're going to do is, if we take our thermometer and we have it sitting there, and what we're going to do is we're going to add a cloth or some piece over top of it that is wet. And that is going to basically be evaporating off of it. And that value is going to measure our wet bulb temperature. And that is, again, just a different temperature. It's going to be a lower temperature than our other temperature. And that value is going to be a wet bulb temperature regardless of the humidity. So the dry bulb temperature is going to be different. If we add extra moisture to the air, the wet bulb temperature isn't actually changing with that added moisture. And we'll see what this is doing later. So just to reiterate, wet bulb temperature is our air temperature when we're fully saturated. So with this, we have a new term. We're going to designate it phi. And this is our relative humidity. And this is a percent. What this is stating is this is a ratio of the current moisture in the air, so the current amount of water, to the maximum. Water that could be in the air if we were 100% saturated. So currently we have a humidity ratio of 30%, meaning that if we had 70% more water in the air, it is going to start raining. So basically, at a specific moisture content, we're going to have water exiting the air. It's going to start raining. And this is how much more water we have to add until we're condensing like so. Oh, sorry. Precipitating and raining are the same thing. I meant to put condensing, but same difference there. And this next term we're going to talk about is omega, which is our specific humidity, or more commonly, the humidity ratio is what I should write this down as. This is more of an absolute measurement of how much water is in the air. So this is how much water is in the air compared to air itself. So this omega is effectively going to be equal to the mass of the vapor in the air divided by the mass of the gas, or the mass of the air in the air. Notice this is not the total mass. This is the mass of the air itself. And what we're actually going to find is a lot of things that we're going to be doing with psychrometrics, we're going to put them in a per mass air basis, not in a per mass total wet moist air basis. We're going to keep track of specifically the amount of air moving through the system. Okay. With this, what we want to do, how we're going to start approaching these is we are going to try to go ahead and get some of these values, and we're going to look at the equations required to make these values. Before we start getting into our other equations, however, we need to talk about Dalton's law of additive pressure. So Dalton's law of additive pressures. Basically, what this is saying is that the volume, so if I have a cube here, of the overall area holding a bunch of gases, this volume is going to be significant compared to the volume of each of the individual gas particles within it. So I've got all these gas particles floating around like so. And in this case, I have a mixture of gas particles floating around. So got some red particles here, all floating around, bouncing around within this volume. And the volume taken up by each of these individual particles is negligible compared to the volume that all these particles are contained within. So the gas particle size themselves, so volume of the gas particles is negligible compared to the volume of the housing. This means if we take our ideal gas law and I'm going to write it in our chemistry form, which is the pressure times our volume is going to be the number of moles of the gas times our R bar times our temperature, I can say that the pressure of a given gas, so let's say the pressure of gas A, is going to be equal to the moles of gas A times R bar of the gas times the temperature divided by the volume. And if I break this piece up a little bit, what's going to happen is R bar is the universal gas constant. So this is going to be 8.314, depending on units, it's a constant for all of the gases within here. My temperature is going to be a constant. It's whatever the temperature of my overall system is. My volume that I'm going to consider here is going to be my total volume. And then my N is by particle. So this means that I can have this partial pressure which I'm calling PA, that is the pressure caused by particle A, or particle A's in this piece. And since I can go through and I can go ahead and say that in the given system there are a total of n moles of particles, that total n is going to be equal to my moles of particle A plus my moles of particle B plus my moles of particle C, so on and so forth. And with that, since the only thing in this equation right here, the only thing in that equation that is dependent, that the pressure is dependent on, is that number of moles, I can then take this equation and say, well, this equation means that my pressure total is going to be equal to my pressure caused by particle A plus my pressure caused by particle B plus my pressure caused by particle C, so on and so forth. Again, this is assuming ideal gases. So we're not quite perfect there, but it's going to make things a whole lot easier. And what it's going to mean for us is that our pressure of our system is going to be a combination of the pressure caused by air and the pressure caused by our water vapor in the air, like that. So this is saying our total pressure is air pressure plus vapor pressure. And that is going to come into play in a couple of our equations here in a second. So, first thing we're going to look at is we're going to go ahead and look at our humidity ratio, our omega. And we said earlier that, or I can actually page back to the slide, we said that our humidity ratio right here was our mass of the vapor within here divided by the mass of our air in here. And with this, not quite using Dalton's yet, but still using our ideal gas assumption. So we can say that the well, we'll go ahead and throw up our normal thermodynamics version. Well, one of our normal thermodynamics versions of this equation. We can say pressure times volume for ideal gas is m times r. This is not r bar. This is r specific to our piece is equal to mRT. So the mass of each of these is going to be equal to our pressure times our volume divided by our R times RT. And I am going to actually convert this R into R bar. So we said that R is going to be equal to R bar divided by the molecular weight, basically switching between moles and grams or kilograms. So I'm going to then have that added in here. So I have pressure times volume times my molecular weight divided by R bar T. And I'm going to take this guy and I'm going to move it up here. And what that is going to do is I have pressure of the vapor, which we said was going to be different, times the molecular weight of the vapor, or molecular weight of water, times our volume. And we said the volume is independent for this. This is where we're getting to Dalton's laws. We're saying this volume of the gas particles is negligible compared to the volume of the housing. So we're just using that total volume of the housing divided by our R bar times our T. And then on the bottom here, we have our pressure of the air times the molecular weight of air, lowercase a, times our volume. Again, we're just using a single volume because of what we said in Dalton's laws. Pressure is right here, divided by our R bar times our T. And with this, what I can point out is that my volumes, I just said, we're using the same volume for this, so the volumes are going to cancel. R bar is a universal gas constant. It's going to work for everything. And our temperatures are the same, so they're going to go away, which is going to give us our final equation, which is our pressure. So our humidity ratio is our vapor pressure divided by our air pressure, or our total times our molecular weight of our vapor, which is the same as molecular weight of water, divided by the molecular weight of air. And that is the same as saying these two values are constants. We can look them up in table A1 of your Fundamentals of Engineering Thermodynamics tables, assuming that whatever version, I'm currently using version 9 of this, but it's table A1 for those that has our molecular weights. And we get our molecular weights overall, saying that these two values come down to a single number. It's just a constant, 0.622 times our vapor pressure divided by our air pressure. And in general, we said that our total pressure, well, our pressure total is right up here. Pressure total is going to be equal to our pressure of our air plus our pressure of the vapor. And we can measure this pressure of the pressure total. We're not going to be able to measure these individual pressures. So we're going to turn this into a form where we can get that pressure of our vapor, and we can get rid of that pressure of our air, which is unmeasurable. So we're going to say 0.622 times our pressure of our vapor which we're going to want for our next piece here, divided by our pressure total minus our pressure of our air. So that's just plugging this equation into the above piece. And basically what we're going to come out to is we have two equations now. We have our definition equation, which is right at the beginning here. Let me get color swap going on here. We have omega is going to be mv over a, and we have our second equation. This is our calculation equation. If we want to calculate omega, we can calculate it with this guy right here. Now, we still don't have, oops. I do have a typo in this equation. This should be minus PV, because I plugged in for PA. I still don't have, as I'm pointing out with that arrow here, I don't have this vapor pressure, which is now showing up two places in the equation. Two places in the equation. And that piece is not something that I currently have. And that is because we're going to use our other value here, our relative humidity, to discuss that and to find that. So going to go back a slide here. And come on, buddy. Talk about my relative humidity. So relative humidity is the ratio of the current water in the air to the maximum water that can be held in the air. So putting that in equation form, what I'm going to do is I'm going to say that this is I'm going to put it in terms as defined by moles. So the number of moles that I currently have of my water vapor divided by the number of, the number of moles total divided, so it's a ratio of number of moles currently in it to the number of moles of vapor when I am saturated, divided by the number of moles total. So these guys are going to cancel. And basically what I'm going to get is this is my equation for the definition of my pressures from Dalton's. So I have a ratio, which is my pressure of my vapor pressure, which is what I'm after up here, and my vapor pressure at saturation. And we know how to find our saturated vapor pressure. This is a value we can find. This is going to be our saturation pressure for vapor, which in our tables is labeled PG, our gas pressure. So this is the pressure of our gas at our saturated state when we're moving between vapor and liquid. So we can say that this guy is going to be equal to our vapor pressure divided by our saturated pressure for liquid vapor, so PG, from tables. Okay, and with that, if we have this guy given, we can use this guy to solve for our vapor pressure and plug it back in order to solve for our omega. Or if we have our omega, we can solve that for our vapor pressure and move it back in and solve for our relative humidity. So we're using our vapor pressure as the piece that is going to move us between these two parts. Okay, one last piece that we want to have in our calculations, and that last piece is going to be our energy of our system. So our energy of our system, we are going to talk about enthalpy. So this part, we don't no longer need our ideal gas law, but we can say the total enthalpy in the system is going to be the enthalpy of the energy controlled by the air plus the enthalpy controlled by the vapor. And I want to define this in specific terms. So I want to say that this H is going to be equal to the mass of my air times my specific enthalpy of my air plus the mass of my vapor times the specific enthalpy of my vapor. And what we're going to do is we want to put this in specific terms as well. We don't want it to be in terms of just kilojoules. We want something that we can use with all of our other equations. We want something that is per unit mass, so we can say that, oh, we have this amount of energy if we're going at this mass flow rate. We have this other amount of energy if we're at this mass flow rate. And we're not going to write, well, this is equal, but we could write this is going to be the mass total times the specific enthalpy total, but we are not going to write this. So this is equal, but we will never use this. Instead, what we're going to do is we're going to put it, like I kind of hinted at before, we're going to put things in terms of per unit air, so per mass air. So if I have air flowing through a system at a certain rate, this is my specific enthalpy term that I'm going to use for my psychrometric equations. So in order to do this, well, sorry, this is not equal here. So what I want is this, I want to use this value, not this value. So in order to make it equal, this would be equal to mass of the air going through times my total enthalpy divided by the mass of the air. So what my equation becomes is I'm going to divide everything by the mass of the air. So I have my total enthalpy divided by mass of air. So this is my specific enthalpy when I'm talking about a psychrometric system, is going to be just my H of my air plus mass of my vapor divided by the mass of my air times HV. And now you see there's a reason that I have a new value for this. So this is just my omega. So this is going to be H of my air plus omega times H of my vapor. And that is why we have our term here. This is why we have our humidity ratio. It makes a lot of our equations a lot easier, so we don't have to consider two mass flow rates. Okay. That was a lot of derivations and a lot of time here, so let's go ahead and put this into action a little bit. So what I want to do is I would like to determine, so I have a system, and that system has a temperature of 40 degrees Celsius, which is going to be a dry bulb temperature. It has a relative humidity of 30%. and it exists in a system where we are at 1 atmosphere of pressure. 1 atmosphere, and I'm going to go ahead and convert that to bar. 1.01325, I believe it is. 25 bar. And I want to know what is my humidity ratio. That is omega. And what is my specific enthalpy at this time, and that is going to be my H per mass air. So the units for this, I'm looking for my kilograms water, kilograms vapor per kilograms air, and here I'm looking for my kilojoules per kilogram air. Okay, starting the problem off. So the first thing that I am asked for is I would like to know omega. Omega I know is going to be equal to mass of my vapor divided by mass of my air. I haven't been given any information about that. And I also know it's going to be equal to 0.622 times my pressure of my vapor divided by my pressure minus my pressure of my vapor. So I don't have my vapor pressure yet either. So I'm going to need to turn to something else for that. And what I'm going to turn to is I'm going to turn to this phi, which I know should be equal to the ratio between my vapor pressure and my saturated pressure. And I can find this saturated pressure. What I'm going to do is I'm going to go to table A2, and I'm going to find my saturated pressure at this 40 degrees Celsius. So this is table A2. This is from our Fundamentals of Engineering Thermodynamics book that we're using for class. And we know we're at a temperature of 40 degrees Celsius. And we have a pressure at our saturated state. So we know that PSat, or PG, depending on how you want to write it, is going to be equal to 0.07384 bar. And this is the pressure during which I'm in the vapor dome, because this is my vapor dome table. This is where I'm talking about I have my energies where I am a liquid and my energies where I'm a vapor. And I'm moving between those. And that whole move between at a temperature of 40 degrees is going to happen at 0.0734 bar. So with that, I'll save some space. I'll throw it down in this next slide here. So I have my phi is going to be equal to my PV divided by my PSat. So my PV is going to be phi times my saturated pressure, which I was given a phi of 30%. 30% is 0.3 times my P saturated, which I just got as 0.07384 bar. that is going to give me a value of 0.022152 bar. I'm going to try to keep from rounding as much here just for our comparison's sake in a little bit. And then with this value, I can take that and I can take this PV and plug it right back up into my omega equation, because that's what I would like to solve for. So solving for my humidity ratio, this is going to be equal to 0.622 times my vapor pressure. This 0.622, I'll throw in units here. I've got space for that. Kilograms H2O per kilogram air. Those are the units that just came out of my derivation, because this was kilograms per mole divided by kilograms per mole. So I have this times my PV divided by my pressure minus my PV. So this is going to be 0.622. I'm just going to write kilograms vapor per kilograms air times my PV is 0.022152 bar. My overall pressure I was given, this is my measured pressure, 1.01325 bar is 1 Pascal. That value minus my PV, which is again 0.022152 bar. And plugging all of that into a calculator, I get a value of 0.0139 kilograms of water per kilogram of air. So this is that first answer to my problem, 0.0139. Okay, and so that guy is solved. I would like my specific enthalpy at this point. So in order to solve for that, I'm going to go to my equation right here. Oops. So I want H divided by mass air is going to be my H of my air plus my humidity ratio times my H of my vapor. My H of my air is going to come from table A22. Again, this is taking from the 9th edition. If this video is being used in the future, you might have a newer version and things may change, specifically in our air tables, because composition of average air changes over time. But for this, I have H of air is, I'm at 40 degrees Celsius. That is 4 degrees plus 273.15 is going to give me 313.15 Kelvin. I have a value for 310 Kelvin right here, a value for 315 Kelvin right here, and I have my H values like so. So with this, if I do a linear interpolation here quickly, I see that I want my value at 315.15 Kelvin minus 313. Something looked around there. 313.15 Kelvin minus 310 Kelvin divided by 315 Kelvin minus 310 Kelvin. I cannot write right now. 310 Kelvin. is going to be equal to the H of air that I'm after minus my 310.24. And this is in kilojoules per kilogram air divided by 315.27 kilojoules per kilogram air minus 310.24 kilojoules per kilogram air. Solving that for HA, I get HA of 313.41 kilojoules per kilogram air. Okay, so this guy is 313.41 kilojoules per kilogram air. My omega I have, that was right down here, 0.0139, 0.0139 kilograms of water per kilograms of air. And then my HV is just going to come from table A2. So HV is going to be vapor. Hg is what it's labeled in my table. 2,574.3. 2,574.3 kilojoules per kilogram of water. You notice that if I throw this all into an equation, H divided by mass of air is going to be equal to 313.41 kilojoules per kilogram air plus 0.0139 kilograms water per kilograms air times 2574.3 kilojoules per kilogram air. My units here are going to go ahead and cancel. So I have my kilograms of water. Whoops, this should be H2O. I don't know, that's a mistype there. Those two are going to cancel out. So this is H2O, giving me kilojoules per kilogram air and kilojoules per kilogram air. So that is going to give me a value for this H of 349.20 kilojoules per kilogram air. Okay, that was a lot of work. And in reality, that is a lot more work than we actually have to do. So that was working it out by hand. What we're going to do is we're going to go down here and we're going to look at another piece from our textbook. So this is figure A9 on page A106 of your Fundamentals of Thermodynamics textbook. And this is our psychrometric chart. Specifically, this is a psychrometric chart for 1 atmosphere, which is why I gave you a question at 1 atmosphere. And what this guy is going to do is it's going to have all of our different pieces on it, and we can just move. If we have 2, we can find anything else we're after. So in our case, I have given you a dry bulb temperature of 40 degrees Celsius. Is our temperature dry bulb. And I have given you a relative humidity of, I believe I gave you a relative humidity of 30%. Let me double check here. Yep, 30% right here. So I can go down here and I can say that I've got a 30% relative humidity. So this guy is my phi. And if you notice, this line is going like so. I can follow that up here. I can follow this line down here. And this is my point on this chart that I'm currently at. And with this, what I can do is I can follow this line to the right, and this is my humidity ratio. So this is my omega. So from the chart, I get a humidity ratio of approximately 0.014, and that is in kilograms water per kilograms of air. So that 0.014, if I go back a couple pages, I had 0.0139. This number is probably a little bit more accurate, but this number took me a whole 20 seconds. So let's stick with that one. And then you'll notice that I have a couple extra pieces on here. One of it is the specific enthalpy of moist air, and you notice kilojoules per kilogram dry air. So this is our H divided by MA, because H is enthalpy in kilojoules. Mass air is kilograms of dry air. And what I'm going to attempt to do here on a screen here, so please bear with me, is draw as straight a line as I can up here. And that is located right around 71, 2, 3, 4, 5, 6 is where I'm drawing that line to. 76. So H divided by mass air is 76 kilojoules per kilogram air. I'm going to address the elephant in the room that this is not the same number that we got a second ago. But before we do that, let me go ahead and point one other piece out. I have my wet bulb, or my saturation temperature in degrees C right here. That's the temperature right there, if I wanted to find that. Okay. With this, this guy is 76. This guy is 349.2. So if I go and I'm going to go ahead and put this on the same page here so I don't have to keep scrolling. So from calculation, H divided by MA was equal to 349.2. Is that correct? 349.20 kilojoules per kilogram air. Okay. These two numbers, not same. That is a problem for us. However, neither number is incorrect. So how enthalpy works is it is not a property that is tied to just the specific situation. It's something where we're going to look at it and we're going to look at a change in enthalpy. We're going to look at how much energy is changed moving from point A to point B, which means that all of these enthalpy values are based off of some base point. So for our chart, you can see that specific enthalpy is 0. At 0 at 0 degrees Celsius with no water. However, if I go back to table A2 and I look at a temperature, this is as close as I have to 0 degrees, Oh, sorry. Wrong thing. Go back to here. I have my, I'm going to switch colors again here. Give me a second. I have my 0 degrees Celsius is equal to 273.15 Kelvin. So 270 Kelvin, 280 Kelvin. My H there is between 270 and 280. I'm just going to go ahead and tell you, if I linear interpolate that, I get a H value for my air of 273.27 kilojoules per kilogram air. And that's because this guy is based off of a system where absolute zero is zero enthalpy. So they're basically based off of different systems. And what that means, if I take this and I take my 349.20 kilojoules per kilogram air, and I subtract my 273.27 kilojoules per kilogram, I get a value of 75.93 kilojoules per kilogram. And that is the same. So these values do work out. It's just if you're looking at a change in energy, you're going to want to look at the change in energy between two things where you do the calculations for both of them, or two things where you use the tables for both of them. You don't want to mix your enthalpies that you pull from the tables and your enthalpies that you pull from pull from your what's the word I'm after here? Energy from your tables and energies from your chart. So, yeah, that was a longer video. Sorry about it, but hopefully gives you kind of an idea of what all of this psychrometric stuff is, what it means. And I'll come back and I'll have a couple of them, probably just one for now for the lab, talking about all of our different calculations that we can do when we're talking about psychrometrics. So hopefully that's helpful. Take care.